Similarly, we read line item. On a line item, we do another map, similar thing, right? Projection and key assignment. And the next step is a match contract. And the match contract will now the join, basically. It will do the concatenation and will set order, key, and shift priority. After that, there will be a reduce and combine contract with partial aggregation and final aggregation. So nothing new for anybody working here in DPF, I'm sure. But the interesting observation here is this is now exposed as a programming model with functional programming. And if you would use it in the query optimizer, the real challenge would be how do you deal with this first order function? Because the first order function that's filter or projection here, it really could be anything, right? And you have to wonder how to cost those functions. So if you were to extend DB2 with such kind of a model, which would not be too hard in my opinion, but for optimization, you would have to worry about assigning cost estimates for those potentially expensive functions. So you might have to do something like black box cost model learning. Now, to look at another example, which is going a little bit away from traditional SQL, but still could be expressed in SQL, of course, is k-means clustering. So how do we do k-means clustering in such a model? So k-means clustering can be done by, I'm a little bit confused. Here we are, good. We would read some data points, which are some input data points, just to give an intuition in that corner. And then, out of those, we would compute cluster centers, or we would just load some initial cluster centers from a file, doesn't matter. So generate them or read them. So we have those blue are the cluster centers. And the next step will now be to actually perform a cross. And what this cross has to do now, it has to compute the distance of each point from the cluster centers. And in this way, we can actually use this, after we have that distance, to do a reduction, which means that we find the nearest cluster center in the reduce step. So that's the function reduce. And the next step then will be to actually do another reduction, which is computing the new centers from those cluster centers that we have determined. And by having done that, we can move the clusters, and now you could iterate over this process, right? That's really how k-means clustering would work. So that's a way of how to define k-means. So that's just giving you some addition, some intuition, how you could use those contracts. Now, let me step down a level in the system and talk about this Nephilim execution engine, which is about now taking those programs and executing them in a parallel way. So this engine executes Nephilim schedules, which are really directed acyclic graphs, which are generated from or compiled from those parallel programs that I just have described to you. So we have this packed compiler, which generates a schedule which is then spanned over the virtualized cluster of computers or the cloud. So the design goals here of the Nephilim system are, on the one hand, to exploit the scalability or flexibility of the virtualized environment, and at the same time provide predictable performance by doing resource allocation while being elastic. So the other goal is, of course, to really have a efficient execution that goes way beyond thousands of nodes by having flexible fault tolerance mechanisms, but at the same time don't pay the price that we currently pay with Hadoop, which writes into the distributed file system every single stage. So we still want to be able to exploit pipelines for short-running requests and don't want to materialize. So Hadoop is doing way too much writing when you analyze Hadoop. They're doing way too much writing in the distributed file system. So it's inherently designed to run on top of an infrastructure as a service cloud and can exploit this on-demand resource allocation. It can even be heterogeneous because we have different types of virtual machines that are supported. There's some characteristics that the scheduler needs here. And actually, we even looking, so we are using the Eucalyptus cloud platform here as an infrastructure, which is basically the Amazon. It's an open source version of the Amazon cloud system. So we actually know the cloud's pricing model, so to know when to add or remove nodes based on some monetary decision. So that's really the goal here. So the architecture has nothing too special. It follows a standard master worker pattern, and the workers can be allocated on demand during processing. So that means while we are operating on a parallelization contract that has been compiled here, we can add or remove nodes dynamically. So it's basically the way the system works, and this shows this little animation. There's a workload over time, and there's 3 workers running right now, for instance, and when the workload goes down, it can actually deallocate some workers, which then are available for some other operations, and then it can bring back workers, and in this way dynamically adjust the performance. And there is a cloud controller that takes care of that. And on the other hand, with the persistent storage. Persistent storage is, right now we are not really focusing in the project on providing our own storage manager. We're just using a distributed file system right now, but of course, and actually we are using the Hadoop distributed file system as is. So we found that HDFS is a very good thing to use. Hadoop we found too restrictive, so for HDFS we were able to take into account here. So now a structure of a nepheles schedule. So a nepheles schedule is said as a DAG where the vertices represent tasks and the edges denote communication channels. So here we have an example which is like some line reader that reads a task and then it writes out some stuff. And there's some mandatory information for each vertex, which is what task program is being executed and what's the input-output data location for the and that's important of course for the I/O vertices only. We'll see there's different types for those communication channels. And there's some optional information that we are using, like the number of subtasks, which is really your degree of parallelism or multi-programming level. The number of subtasks per virtual machine, the number of virtual machines, the type of the virtual machine, how many CPU cores, RAM and whatnot, the channel types, and how the virtual memory is shared among tasks. And this schedule is converted into an internal representation. This internal representation then has now the parallelization made explicit. So we are spanning basically a tree and identify the parallelization range for each operation. So the multi-programming level is derived for each parallelization contract. And we also derive the wiring of the subtasks and how the communication flows from those parallelization contracts, because we have to fulfill those contracts, right? We have to make sure that we process the merge or the co-group pact or the map pact correctly, right? You can set the clear parallelism. And the nice thing is that can even be done adaptively, right? Because we are adaptive, so we can say, based on the input of the previous stage, we can actually determine the degree of parallelism. So then we do an explicit assignment to virtual machines. So like in this case, we have here two virtual machines, like some small machines, some large machines, so we can distinguish based on some machine type, which depend on a certain hardware profile. And that's then how the execution can take place. However, there's some issues with this on-demand allocation. So the question is really, when should we allocate virtual machines, right? Because you may need more virtual machines for the next stage, so you need to be sure that those are available. And when should we allocate them? And in general, you don't really have this guarantee of the resource availability. And in order to overcome that, we have introduced into nepheles a concept which we call stages.